In this video, we are going to talk about parameterized surfaces and surface integrals. So in previous videos, we talked about parameterized curves, and then we did line integrals. So this is the analogy, except with one more dimension added on. So what we will do is go through this overview slide sort of quickly, and then we'll go through each topic with more illustrations, more detail, and examples. And then at the end, there'll be more examples and some problems for you to try. So we were going to start by defining what a parameterized surface is. We're going to think of a surface as being obtained from a plane by rolling, bending, and pushing. For example, to get a torus, this donut shape, we can think of taking a portion of a plane. In this case, we're going to think of it like a piece of paper, and we're going to roll it and then rolling it up into a tube and then bringing the ends together until they meet, until you get this donut shape. So again, the surface takes a two-dimensional shape and then it produces something in 3 dimensions by some sort of manipulation, and our manipulation is our function. Another way to think of this mathematically, but sort of using the same sort of ideas, is a parameterized surface is a function. And the function we call phi, and it takes something in 2 dimensions. And here, so it's part of a plane. Here we said the plane was the piece of paper. Here we have the UV plane, and we have a portion of it that we consider our domain that I have shaded in yellow. So a part of R2, and then we're going to kind of push and bend and throw it up in the air, sort of like this is pizza dough on a counter that you might have rolled out in this funky shape. You're going to throw it in the air, and by some fanciful coincidence in R3, it's going to take this 3-dimensional shape in R3. And so we define phi, that's the mapping that goes from this 2-dimensional shape to this 3-dimensional shape. And again, it takes a u and a v, so we're in a UV plane, and it defines an x, a y, and a z coordinate. So again, phi is the map to get the surface twist or bend a region in the plane to yield a surface. And I'm also going to give you a warning. When I first did this series of videos, I did it when I was talking to my daughter who was in college at the time, and I couldn't remember what this Greek letter was called. So it reminded me of the Green Lantern from the comics. So I used to call it the lantern function. So if I inadvertently call it the lantern or I miss updating something, you might hear me call it the lantern and no one else calls it the lantern function. Know that I mean phi, and that phi looks like the Green Lantern symbol. Anyway, going on, we also have t subscript v, and that's the vector tangent to the curve when we fix u equals u naught, and then we have the mapping phi of u naught v. So in other words, we take a fixed value of u, and here it'll be, some line at u equals u naught, and then that same line gets mapped to some line here in 3 dimensions. That will be our tangent vector, tv. And then on the u, oh, that was tv, I'm sorry. So holding v fixed, throwing it up in the air, you'll get some vector. You can do the same thing for u. Hold u constant, map that line, that constant line, and that'll give you the tangent vector tu. When you cross tu and tv, because the thing about u and v is they're perpendicular to each other, whatever 2 lines you choose, they'll be perpendicular. When you cross them, then you're going to get the vector normal. So tu cross tv, here it is the vector normal, right? Because you have tu, which is on the surface. So you're going to have tu, which is a vector on the surface, tv is a vector on the surface. What we know by a cross product, if you have 2 vectors, you cross it, you're going to get a vector that's perpendicular to both. So tu cross tv will be our vector normal, and therefore we can get the equation of the tangent plane, which is x minus x naught, y minus y naught, z minus z naught dot n. So this equation, as well as the fact that tu cross tv is normal, that is things that we talked about when we had our video on the cross product. And we can also say that the surface is smooth if tu cross tv does not equal to 0. We have this example now of a surface, and this is a surface of a cone. There are a couple of surfaces that you should be really familiar with, which is the sphere, the cone, the cylinder, and I can't think of anything else right now, but we'll think about that later more. Oh, a cube. Those are surfaces that appear over and over from now until the end of the book. So this is one of them, the cone. Z squared equals x squared plus y squared defines a cone. And actually we did talk about this a little bit in chapter 2 when we talked about graphing functions. But we'll talk about parameterizing a cone now. So we can think in 2 dimensions. We can have a theta coordinate and an r coordinate. And then, that's in the plane. It'll define an area in the plane. And then phi will take our theta and an r coordinate, and it'll produce an x, y, and z coordinate. In this case, you can see that the z is equal to r, which is the square root of x squared plus y squared. So this tells you that you get the cone, and we'll kind of illustrate that later in this video. We can also calculate then TR, that's the partial derivative. I forgot to tell you this. So TV is the partial derivative with respect to x, with respect to y, with respect to z. So we can calculate TR and T theta, do the cross product, and here is our vector normal to any point on the cone. And now that we've done a quick run through of our overview slide, we'll go through each topic in more detail with more examples. To start, we should get an idea of what a surface is. So a surface, we should think of it as something we can obtain from a plane or a portion of the plane. And we can then roll, bend, or push this plane, mold it into a shape. So for example, to get a torus, this donut shape, we take a portion of the plane, we roll it up, we take the ends, bring them together until they meet, and we get this torus. So when I say we take a portion of the plane, we can think of this UV plane, and here we have a domain, or a section of the UV plane, and then we somehow twist and map it or stretch it and map it into this surface here. And all the twisting and bending and stretching we do is considered a mapping. We will call the mapping phi, and again, it takes this 2-dimensional region in R2 here, and it gets contorted or stretched, pulled into something in R3. So it makes this little 3D sculpture, and we said S, and so it's a surface now, and we say S is equal to phi of our domain. And again, we consider this a surface. It's kind of flat, but it contorts in 2D, and also you definitely have sides, a top side and an underneath side of this surface. I don't know why, whenever I think of taking something on the plane and throwing it into the air and getting this other surface, I think of people making pizza dough, like you roll it out on your cutting board and then you throw it up, you toss it up, the pizza tossers, and then you get this other shape. Admittedly, the probability of tossing some pizza dough in the air and taking a shape that we parameterize, like a sphere or a cylinder or a cone, is very low. So you might prefer to think of this as like rolling out a piece of clay on a table or other flat surface, and then a sculptor comes along and lifts it up into 3-dimensional space and then sculpts it into some nice shape. Okay, so now that we have the shape up in the air in 3-dimensional space, we can start talking about tangent vectors. And if I look at this, I can take the tangent vector by looking at a fixed value of u. So for example, here, I might say this is my u naught, and there's a line that goes through here through our domain. And when we map it, it might go something like this on our surface. I can do the same thing in the v-plane. I can pick a fixed v, maybe here, and then when I map it, it might map to something like this here. Looking at this with respect to partial derivatives, so my tv vector here is essentially my x, y, and z vector taken partial derivatives with respect to v. And then my u, my tu, is going to be the partial derivatives of x, y, and z taken with respect to u. So here I have my tv, that's my tangent vector at v, and my tangent vector at u. So I have my tangent vector with respect to u, my tangent vector with respect to v, so they're both on the same surface. They'll both be in the same plane. So when I cross them, tu cross tv is going to be a vector normal to the surface at that point. And from our video about cross products, we know when you take the cross product of TU and TV, so this is the vector TU and TV, that the resulting vector will be perpendicular to both TU and TV. And since these two vectors are on the are on the surface, then right at the intersection U naught V naught, there's this plane that's tangent, and TU cross TV will be normal to that surface since TU cross TV is perpendicular to both TU and TV. Therefore, the equation of the tangent plane is going to be x minus x naught, y minus y naught, z minus z naught dot n, our normal vector, which is TU cross TV. And one last theorem, the surface is smooth if TU cross TV equals 0. Next, we'll go through the example of parameterizing a cone, and we have z squared equals x squared plus y squared defines a cone. And if you need a little bit of a refresher, remember we used to do the level curve, so we would look at z squared equals x squared plus y squared, and we'd say, well, what happens when z is equal to 0? So we're down here on the xy plane. Well, then x squared plus y squared, we're at 0, 0, so we get a single point. When z squared is equal to 4, so z is equal to 2, so we're up a little bit higher right now. And then we have that, and so in z, we've come up to the point 2 for z equals 2, and we see that z squared is equal to x squared plus y squared. Well, the x squared plus y squared terms are giving us a circle of radius 2. So that would be over here, we have this circle of radius 2. And I didn't mean to fill in the inside. It's just the circle of radius 2. Then when we have z equals 9, as we go up higher, then we have x squared plus y squared is equal to 9. So we have this circle over here of radius 3. Similarly, we can do the same thing for negative values of z, and we'll get the upside down cone. So now that we remember how this z squared plus x squared plus y squared defines a cone, we can parameterize our cone using polar coordinates. And we choose polar coordinates because of the geometry of the situation, right? It involves a lot of circles. So our phi function of theta r is going to be r cosine theta, r sine theta. This gives us the different circles with different radiuses, and then also z is equal to r. And just to remind you why that's the case, by this here, z is equal to square root of x squared plus y squared. Plugging this in, then we get z is equal to r. So what we're saying is we take this portion of our plane where we have theta and r, that's how our plane is defined, theta from 0 to 2 pi and r from 0 to whatever the radius is, and we use our lantern function and we get this cone. I can also calculate my normal. I need to take my partials with respect to r. So I come over to phi, the partial derivative with respect to r, considering theta now a constant. So with respect to r, I'm just going to get the constant, cosine theta. Here, derivative of with respect to r, I'm just going to get the constant sine theta. Derivative with respect to r, I get 1. Next, I take the partials with respect to the tangential line with respect to theta. So now r is considered a constant, theta is considered our variable. Derivative with respect to theta is minus r sine theta. This is minus r cosine theta, and this is 0. To get my normal, I take the cross product, tr cross t theta, and I'm going to end up with minus r cosine theta, minus r sine theta, and r. So that's it for the main ideas of this video. I have a couple more examples dealing with these tangent vectors in the normal, and then I have some very important other examples, a parameterization of a sphere, of a cube, and of a cylinder for you. Again, those will become very important, so I suggest you take a look at those. My first example is if I have phi is equal to u cosine v, u sine v, u squared plus v squared, where does the tangent plane exist? And find the tangent plane at phi 1, 0. So the first thing I'm going to do is start by taking the partial derivative of my lantern function with respect to u, the partial derivatives with respect to v. So I have my tangent u, tangent v, and then I do my cross product to find my normal. And I should get in the habit of writing in to remind myself that's the normal. And this is what I get. Now, if I want to know where the tangent plane exists, then I'm going to use this theorem here. So I'm going to look to see where T of U cross T of V is equal to 0. And I'm looking to see where T of U and T cross T of V is equal to 0 because by this theorem, the surface is smooth if T of U cross T of V is not equal to 0. When I look at this, it's equal to 0 only when cosine and sine are both equal to 0. That means we're at the point 0, 0. So there's no tangent plane at the point 0, 0. All other points have a tangent plane. Next, if I want to find the tangent plane at my lantern of 0, 1, the first thing I can do is calculate my tangent, or my normal, I'm sorry. I should write this as the normal next to TU cross TV. At the point 0, 1, I plug that in, and I'm going to get minus 2, 0, and 1. I also need my lantern of 1, 0, so I plug that into my lantern function, and I get 1 times cosine 0, 1 plus sine of v, which is 0, and then 1 squared plus 0 squared, which is 1, 0, 1. So I have my normal, and I have my point on the plane. So if you recall, the way we're going to find the equation of the plane is that this is the vector normal. Then when we dot a line on the plane with the normal, we're going to get 0. So here I have a point on the plane, but if I take a representative element x, y, z, and I can write the line between x, y, z and 1, 0, 1 as x minus 1, y minus 0, and z minus 1. I can dot it with my normal, and I set it equal to 0, and what that tells me is my minus 2 plus 2 plus 0 times this plus 1 times z minus 1 is equal to 0, which means that I get z is equal to 2x minus 1, and that will be my tangent plane. Our next example will be to parameterize the surface of a sphere. We'll back up a little bit and review how to parameterize an entire sphere, including the interior and the surface. So if our sphere is of radius rho, then the x-coordinate will be rho cosine theta sine phi, the y-coordinate is rho sine theta sine phi, and the z-coordinate is cosine phi, where theta goes between 0 and 2 pi, phi goes between 0 pi, and rho goes between 0 and r being the radius. You can see in this parameterization that we include the interior. In fact, we start at rho, the radius is equal to 0, so we have this point at the very middle, and then rho increases until it gets to our r. So to do just the surface of the unit sphere, and by surface I mean if you picture the sphere as like a bubble, a soap bubble, then I only want the soap film on the outside of the bubble. Or if you have a basketball, I only want the material making the basketball. I don't want the air inside. So in other words, I don't want the radius to go from 0 to r. I just want the radius to be fixed at r. In this case, since we're parameterizing a unit sphere, the radius, or rho, is equal to 1. So my parameterization of the unit sphere only depends on theta and phi. Again, rho is fixed at 1. So I have 1 cosine theta sine phi, 1 sine theta sine phi, 1 cosine phi. Our parameterization, again, is only dependent on theta and phi. So now I can take the tangent vector with respect to theta. So taking the derivative of this parameterization with respect to theta is going to give me my negative sign. My sine phi is held constant. Here I'm going to have my cosine theta, and my sine phi is held constant, and then this is 0. Similarly, I can take the tangent vector with respect to phi. So now my thetas are held constant, cosine theta, and this will be cosine phi, sine theta, cosine phi, and this will be minus sine phi. I can get my normal by taking my cross product of the phi with respect to theta here. So respect to theta, sine phi is considered a constant. So we have the derivative of cosine theta is minus sine theta sine phi. Here we're going to have cosine theta sine phi. And here with respect to theta, This is just a constant, so it's 0. Then I take my derivative with respect to phi. Is it phi? Yeah, phi. I have to remember phi versus phi. So phi, so now my cosine theta is considered a constant. So I have cosine theta, cosine phi, sine theta, cosine phi, and then this will be minus sine phi. I do my my cross product, and I end up with minus cosine theta sine squared phi minus sine theta sine squared phi minus sine phi cosine phi. Next, we're going to parameterize the surface of a cylinder. To remind you what the cylinder looks like, that's r cosine theta, r sine theta. This gives you the circle of radius r, and we're going to hold r fixed. We're not going to worry about r going from 0 to r because we don't want the interior, just the surface. So here, r cosine theta, r sine theta is just the circle. And then z tells us we're going to take the circle up from z equals whatever the z parameter is. This z, if it goes to infinity, it's infinitely large. And again, theta goes from 0 to 2 pi. So if we only want the cylinder of a surface of a cylinder of radius a, then our phi of theta z is going to be a cosine theta, a sine theta. Again, we're holding r fixed at a. And then z, where theta goes between 0 and 2 pi, so we get the entire circle, and then z will go between 0 and h because we have a height of h. So we can imagine this as taking a plane, a sheet of paper in the plane of height h, and then the circumference of the circle is 2 pi times the radius a. So this will give us the circumference, and we just roll it up, and this blue line could maybe be this blue line here on the cylinder. The next parameterization we're going to do is parameterization of a cube. So the cube is going to be our first surface that we consider a union of several surfaces. In fact, in this case, we're going to take the 6 faces of the cube and parameterize each one individually, and then say the cube is the sum or the union of those 6 faces. I will parameterize this surface here outlined in yellow for you, as well as the surface here outlined in green. I'll call the first surface S1, the green one S2. And then as an exercise, I'll have you try parameterizing the surface for S3 and S4, and I'll give you the solutions to that. And hopefully after that, you would be able to do the remaining bottom surface and this other surface in the back. Looking at this first S1 surface, this yellow surface, this is at x equals 1. Remember, this is the unit cube. I guess I should have said unit cube. So this is at x equals 1. And it's x equals 1 for the entire yellow surface. So our phi only depends on y and z. So x is equal to 1, y and z, they can vary between 0 and 1. That'll give us this whole, now y is going to go between 0 and 1, z is going between 0 and 1. For this S2 surface, this green surface, this surface sits on the line y equals 0. So y is going to be held fixed at 0, where x and z can vary between 0 and 1 to give us this surface, this square surface. For this S2 surface, I went ahead and compute the normal. First, I want the phi with respect to x. So here, this is 1, 0, and 0. If I take the partial derivatives now of phi with respect to z, because our two variables are x and z, so with respect to z would get 0, 0, and 1. Now I can take the normal by taking the cross product, and I get 0, negative 1, 0. So what that means is over here, for our S2 surface, the green face here, that our normal is pointing outwards in the direction of 0, negative 1, 0. So that means, in other words, it's pointing in the negative y direction, which is exactly what we would expect. As I have mentioned, I left S3 and S4 as an exercise for you, and then I also have the solutions for you. To review the ideas we have talked about on a parameterized surface, so a parameterized surface takes a portion of the plane, and it stretches or rolls, bends, pushes, until we get something in 3 dimensions. So the idea is here, In the UV plane, we have a portion of the plane, which is our domain, and then our phi takes this portion and twists it until it becomes a 3D sculpture over here, work of art. So our surface now is the mapping phi on our domain. We can calculate then a tangent vector to this curve of our surface by looking at holding u constant and then seeing where that goes. That would be the partial derivative with respect to u, and we can fix v and get the partial derivative with respect to v. So tv is dx dv, dy dv, and dz dv, and tu is dx du, dy du, and dz du. And then what we can do is then take tu cross tv and find a vector normal to the surface at uv. So in other words, when we cross the product, we get something that's normal to vector on the surface and the vector tv on the surface, and then our cross product will give us something that is normal to both of these vectors and normal to the surface at that point. Therefore, the tangent plane is equal to x minus x naught, y minus y naught, z minus z naught dot n. We also looked at parameterization of the cone as well as the unit sphere, the surface of a unit sphere, the surface of a cylinder of radius a, height h, and then also the unit cube. And those three surfaces, as well as this parameterization of a cone, are things that you should be familiar with because they'll keep popping up from now until the end of the book. For review, I have these three problems. The first one is to suppose a surface S is the graph of a differentiable function g that goes from R2 to R3. Show that the surface is smooth at all points u0, v0, g of u0, v0. The second, parameterize the S3 and S4 surfaces of the unit cube shown. And the third, calculate t of theta cross t of z for the surface of a cylinder of radius a. I'm going to suggest you pause the video, give the problems a try, and on the next slide I'll have solutions for you. Here are the solutions. And that is it for this video. Thank you for watching.